So when we're computing the regression equation, we're going to be using the same process that we did to hand calculate a correlation. In other words, we're still looking at the sum of products for both of our predictors and the sum of squares. So again, the sum of products is the combination, the sums of squares for x and the sums of squares of y. So that process has not changed. However, we're now using it to create some additional equations. So again, remember that y is the outcome or the dependent variable. It's what we're predicting, and x is the predictor or the independent variable. So one of the things we need to calculate is slope, and you may see different equations, but basically they're all calculating the same thing, and that is sum of products divided by sums of squares x. So again, the sum of products is each individual score minus the mean of both the predictor and the outcome multiplied and then added together, divided by each individual score on x, our predictor minus the mean, squared and added together. That's actually going to create what we need to figure out as far as our slope. Now the y-intercept is simply going to be the mean of y minus b once we've calculated it times the mean of the predictor. So the mean of our outcome minus the mean of our predictor, x, multiplied by that b weight. And again, I really want to stress the difference between beta, which is the test statistic of regression, and little b, or b weight, which is actually a part of the regression equation. So let's go through the computations again. So we're computing the regression equation. What is the relationship with the regression equation that defines the relationship between hours spent studying and test scores? So we're back to those same old scores that we had before, and we're going to calculate, again, the sums of products and the sums of squares x to move forward. So again, this should look familiar from last week's lecture. We have our individual scores on x, our predictor, our individual scores on y. We're going to sum those and divide it by the number of scores that we had to get our mean for x and our mean for y. In this case, the mean for x is 6, the mean for y is 60. We're then going to calculate each individual scores minus the mean of the predictor, x, and each individual score on y, the outcome, minus the mean of y. We're then going to take those numbers and use them to calculate both the sum of products, each individual score minus the mean of that score, multiplied by their score on their outcome, y minus the mean of y, and also the sum of squares for x, which again is simply x minus the mean and squared each time. And we're going to add these up to again get the sum of products and the sum of squares. In this case, walking through that equation, we're going to find that again, our sum of products is 420, and our sum of squares x is 64. So again, to calculate b, we're simply going to take those numbers and put them into the equation, and once we have b, we're going to use the means to figure out the y-intercept. So moving on to the next slide. Again, the sum of products was 420. It goes on the top of the equation, and the sum of squares x was 64. 420 divided by 64 is 6.5625. And again, we would round that to 6.56. Generally speaking, we want to follow APA guidelines on rounding and always round to the second decimal point just for consistency and simplicity. But again, I'm putting it out there in a greater form so that you can also check your own answers as you walk through this with your calculators and your hand calculations. Once we have the b weight, so b weight again is the unit change in y for each 1 unit increase in x. So now we need to compute the y-intercept. And again, it's simply the mean of our predictor, our mean of our outcome, y, 60, minus the mean of our predictor, in this case x, 6, multiplied by the b weight. So again, we plug those numbers in the equation, we calculate it, and we find out that our y-intercept, what would it be? What test score would we expect if someone actually studied 0 hours? And the result of that is 20.625. Again, we'd round it to 20.63. So that tells us if someone studied not at all, we'd expect them to get basically a 20. If they studied 1 hour, we'd expect them to get approximately a 26 or 27. If they stored 2 hours and on forward. So our prediction equation, y predicted, would be that, again, that constant a, 20.625 or 20.63, times, or I'm sorry, not times, added the b weight multiplied times the actual score the person had. So again, if someone studied 10 hours, we'd multiply 10 by 6.5625. We then add that to 20.625, and that would be our prediction of how they would do on the score on the test. We'd expect them to do approximately an 85 or 86, just doing the quick math there in my head. So again, this is where we're getting the additional information from the regression equation. We're running through the same process we would with correlation to make sure there is a relationship and it's significant, but then we're also calculating both the B weight and the y-intercept, allowing us to make prediction. Now, once again, we're getting all of these numbers from a sample where we have both their y-scores and their x-scores. They're known values, and we know the relationship between them, and therefore we're calculating this line of best fit based on these equations. But what we'd use these equations for is in a new sample or new individuals that we only have their predictor score in order for us to predict what their outcome would likely be. And for that, we also need to then determine how accurate is our estimations. And to calculate that, we need to calculate the standard error of the estimate. Now remember when we talked about the regression equation, the initial regression equation that I submitted to you was y plus a constant, or y equals a plus or minus b weight times x plus or minus error. Now we don't know error for sure, but we can estimate error, and that's what this is, the standard error of the estimate. It gives a measure of the standard distance between the regression line and the actual data points. It gives us a range, in other words. So it's the amount of error from the data points to the regression line. It's kind of like a standard deviation, but for prediction of the regression. And it also determines how good that regression line is. Now again, there's multiple ways to calculate this. I have two of the equations, but effectively we're doing the sum of y, each person's actual score in the outcome, again from our original sample, minus what we would have predicted their score to be. We're going to square that and we're going to add it up. Then we're going to divide by n minus 2, the number of participants minus 2, and then we're going to take the square root, and that will become the standard error of the estimate. You may see the equation on the right in some textbooks. This will get you the same answer, but I'm trying to go with equations that are already following the process that we've done before. So we're not having to do really a new type of math or bring in numbers from other places. So how do we actually calculate this? Again, we need to make a table. So we've got the actual scores on Y. We know the scores on Y. We have a real sample. We know how people performed the test. We've got a 30, a 90, a 30, a 60, and a 90. But then we're going to actually do our prediction. So we're going to take for each individual person, how many hours do they study, and run it through to create a Y prime. So for example, the person that studied 0 hours, we would have actually expected to get A. We would have expected just the intercept, 20.625, which is below what they scored. The person that scored a 90, we would have expected them to score an 86. The person that scored a 30, we would have expected, again, by their study hours, to have actually scored a 46. And the person that scored a 60 and a 90, by their number of hours studied, we would have expected 73s. So you can see how, though there is a pattern, and though we are better than guessing when we use study time to predict, it's also not giving us an exact prediction. So to calculate the standard error of the estimate, what we need to do is take each person's actual score minus their predicted score and then square it. So for the top line, we're going to take 30 minus 20.625. That's going to be 9.375. We're going to square that. That's 87.89. We're going to do that for each individual score, and then we're going to sum it. We're going to add it up. And that turns out to be 843.75. Now again, we had 5 total participants, so our n was 5. 5 minus 2 is 3. We're going to take 843.75 divided by 3, and finally that number, we're going to take the square root. Turns out it's 16.77, which that now tells us that on average, if we predict someone to have a score, their score is very likely to fall within the range of that prediction plus or minus 16.77. So if I say you're going to get a 50, I'm pretty confident that you're going to score somewhere between actually a 66.77 and going the other way, what is that, 33.23? I think so. 32.33. So anyway, that gives us both the prediction but also a range of accuracy. And we want that as well if we're making estimates and we're making predictions. So again, the smaller the C, the smaller the scatter plot, the closer the actual predictions were to the actual scores. The larger the C, we still can use it for prediction, but it's also telling us that any particular line, if we actually looked at any particular exam score by study time, we'd find that study time, though it's related, our prediction is not perfect, and in fact there is some error in it. So the larger the C, the less we can rely on our predictions, but we still get the same information from the standard error of the estimate. It basically gives us the range that we could expect to see a score fall within on that prediction.